Okay, chemistry. Today we're going to talk a little bit about the kinetic molecular theory. Now really this is a theory that is dealing with gases. And you should have probably already read some in the book to get started and have some notes. So this is just an addition to what you currently have. Now to kind of get started, I want to talk a little bit about our phases first. So this would be an example of seen as solid molecule or solid substance. And so let's just say that this solid substance here has some molecules that are kind of locked into place. It's like a crystal structure. Now what we generally see is with these solid substances, these molecules themselves are doing a little bit of vibration. So they're actually trying to move a little bit, but they can't move a lot because they're locked into place. Now as we transition into a new phase, think of like the liquid phase. All right, now I got to have a container to kind of put my substance in, and now all of a sudden our molecules are no longer locked into place. They're kind of free to flow about. So we see them more in a random pattern. Now this is what allows us to kind of flow through things. They're able to kind of bump into each other, but in a sense they take on the shape of their container. It isn't until we move into the next phase that we really see all of a sudden our substance that was in our container, so I'll just draw in our substance here, is now trying to exit out of here and get into the gas phase. Now once we're in the gas phase, you're going to notice that we end up having more space in between each of these, and that they're kind of moving in directions based on their motion. So this is really what we're looking at when we get into our gas phase. Now we talked about this earlier in class, so I wanted to just touch base on that. But really we want to start to get into the principles then of the kinetic molecular theory. So that big space thing that we see in here, so large space, is one of the principal things that we see in the kinetic molecular theory. It's one of those. Now what we really see from this is we see that we have a greater densities, or excuse me, a less dense material. So in other words, that space creates that more volume that we have per unit mass. So we see that our density is going to be a lot less when we do this. We also can see that from this large space, we've got the ability to make compression, that we can actually compress all these gases into our container. So if we see a container of gas, we can actually do some compression. We can't do that with either the solid phase or the liquid phase. Only in the gas phase can we do that compression. Now, along with that, we know that these objects or these molecules are in kind of a motion, constant motion. So when we start to look at this constant motion, and this motion's fairly random, it's kind of every molecule is moving along. You have to remember though that it's moving in kind of a straight line. Now what that leads us to is some kinetic energy. So all objects that are in motion have some kind of kinetic energy associated with it. That kinetic energy usually takes on a relationship that is 1/2 mv squared. So you can see that if that molecule has a mass, which all molecules do, and have a velocity, this V stands for velocity, we know that there's energy associated with that molecule. So in other words, we see energy. And that energy is something that's measurable. Let's see. When we look at the other thing, we'll see that there's going to be some collisions involved. So as the molecule is moving along, it can collide with the wall of the container, or it can collide with each other. But whenever those collisions happen, we expect those collisions to be elastic. Now what an elastic collision is, it just means that we're not going to lose any energy in our reaction or in our collision. So all of the energy is going to be maintained as well as all the momentum. So we see that whenever we have those situations. Now we also expect there to be no forces at play when it comes to this. So no attractive forces. So every molecule that's moving along doesn't have any attractive forces acting on it. So really when we look at this, this is what we refer to as kind of the kinetic molecular theory. Now I think in your notes you probably had 5 postulates. So one of the postulates was about the large spaces. One was about the constant random motion. We probably had another one that was about the kinetic energy associated with it. Another one that was about the collisions, and one about the forces. Now all of this kind of goes together to give us this concept of what a gas really is. So when we see this, we expect this to be what we call an ideal gas. So this is a gas that would perfectly adhere to all of these postulates of the kinetic molecular theory. Now the reality is that we don't have a lot of ideal gases. We really have some real gases, and these are gases that we would deal with in lab all the time. So there's usually some variation from the theory into reality. Now where we usually see that is probably in here with our forces of attraction. So usually if you have a molecule, if it's a polar type molecule, there's going to be a small amount of traction with it. So in other words, the molecules might try to stick together a little bit. The collisions are probably not going to be perfectly elastic. And if it's not a perfectly elastic collision, that means that we're probably losing a little bit of energy. So all of this is great if we're talking about an ideal gas, but the reality is that we're usually dealing with a real gas, and usually there's a little variation due to forces or collisions, and that varies our energies. So that's usually what we end up seeing when we look at real gases. Now, one of the things that you guys did yesterday, or I should say not yesterday, but in the last activity, was you looked at some various types of quantities that deal with gases. So let's look at a couple of these quantities. So our quantities for gases are really going to be 4 of them. The first one is always going to be volume. So we always like to look at volume. And when we start to look at volume in all of our situations, we want the units to be in liters. Okay, so we're going to usually measure our volume in liters, and that's because of the amount of space that these molecules take up. Remember, there's a large space, so we want there to be volume that's going to be appropriate. So we're going to talk about them in liters. The second one that we're going to look at is going to be temperature. Now temperature is an interesting one because that quantity is really a connection back to the kinetic energy. So we really see this as something that connects to our kinetic energy. So it connects us back to kinetic energy. In fact, it's the average measure of that kinetic energy. So if you think about all of the molecules that are moving around, all have maybe some slightly different speeds. Well, if we averaged all those speeds together, that would give us the average amount of kinetic energy that a substance would have. So that's our temperature connection back here is about the kinetic energy. Now, typically when we start to see units for temperature, we're going to deal with the Kelvin scale. Now, the Kelvin scale is an absolute scale. So it starts at 0, and it only gets positive, okay? And it goes up from there. So that's the Kelvin scale. Now, we also tend to see the other scale in science, which is our Celsius scale. And remember that the Celsius scale starts with a 0 degrees Celsius for freezing water and 100 degrees Celsius for boiling. Now, the one that you're probably most familiar with is our Fahrenheit scale, which is 32 degrees Fahrenheit and 212 degrees Fahrenheit for that boiling and freezing points of water. Now, that's the three different scales that we tend to see. And we have a relationship that we can do to convert between those temperatures. I'm just checking to see if it is. We do have the one relationship on your green sheet that says that a Kelvin temperature is equal to a Celsius temperature when we just add 273 to it. So that's one of the ways that we convert between Celsius and Kelvin. So be aware that you have a way to connect between those two. Okay. The other quantity that we like to deal with is going to be this kind of a new one. It's going to be the pressure. Now, pressure really comes back to a concept that we look at, which is called force per area. So pressure is the force that we apply on the surface area that we're applying that. So if we think about the molecule as it's moving along, so we've got a gas particle, okay? Here's our gas particle, and it's moving along, so it's got some motion to it, and it's going to interact with the wall of a container, okay? As it comes in and hits the container, it applies a force to that container in that specific area. And if you have enough of these going on, that means that you create pressure. So if you think about it, it's a little bit like what we would consider inside of a balloon. So if the wall of my container is actually a balloon, so let's just do this. There's our balloon. We have molecules that are moving around here, and they are trying to interact with the walls of the container, so they're putting pressure on it. And sometimes those are moving away from the wall, but there are other times there's ones moving towards the wall. So in other words, these molecules are constantly in motion and constantly pushing on the wall of the container to create that amount of pressure that we see in this. So this is what makes a balloon expand. So really, that's a kind of pressure is an important role when we start to get into gases. Now, when we start to look at the various units, traditionally, we probably would look at this in terms of ATMs, okay, which is actually an atmosphere, but we could also have a unit called kilopascals or a Pascal, and we probably go to kilopascals to make it bigger, and then we also have the millimeter of mercury. So all of these different unit types are listed here on your periodic table, or on your green sheet. So like 1 ATM is the equivalent of 101,300 pascals, or 101.3 kilopascals, or 760 millimeters of mercury, and then there's one other unit, it's the 760 torr. So these are just all equivalences so that you can do a conversion to get between them. You would just do dimensional analysis to do this. Let's see. I do like to kind of talk a little bit about how we measure pressure. So like if we were to measure pressure, we're going to look at it in terms of a device called a barometer. So a barometer is really this. I'm going to have a little bit of a dish, and we're going to put some kind of a liquid inside this dish. And this liquid could be anything. when they first did this, they used mercury. And then inside this, you would probably invert some kind of a glass tube. So we've got a glass tube. And so what happens here is as the air pushes down, so in other words, we have air that's trying to push down on this surface. And that's creating that force per unit area. It's going to force the liquid to rise. So we might see that the liquid now moves up to this. So as we get an increase in our force on the outside of the liquid, it forces the liquid in the tube to rise up. And so this is how kind of a barometer works. So a barometer works by exterior pressure acting on it. So when the barometer is rising, it means that there's going to be higher pressure on the outside, and that's being shown here by the inside. So in other words, we could see or measure this to be like, I don't know, 775 millimeters of mercury. And in mercury was the traditional liquid that we used, which is exactly why we're measuring it in millimeters of mercury. So they would say from here to there is 775 millimeters. If we all of a sudden saw the air pressure lower, so the air pressure lowered, that means that the mercury would drop, and we would again just measure the distance between the dish and that would tell us what the pressure would be. Now, the barometer was invented by an Italian scientist named Torricelli, and that's why the other unit that you tend to see here is called a torr. So that was named after Torricelli. So this is about how a barometer works. Now, the other thing that I wanted to just talk a little bit about was the various units and how those units interacted. So again, we look at it in terms of, switch to a different sheet here. We looked at it in terms of those 4 different quantities. So 1, 2, 3. Oh, the 4th quantity. I didn't even mention what the 4th quantity was. Hold on, let's go back there. Our 4th quantity is actually the amount. Okay, the amount of the particles that we see. So it's the number of particles. Now, traditionally, this would be measured in moles. Oops. Because we already know that if we have moles, that's the same as number of things. So our amount is based in moles. So we've got really 4 quantities that we like to deal with: volume, temperature, pressure, and amount. We're going to kind of focus on these because I think these are the ones that you used in your simulation. So let's talk about those relationships. Okay, so again, we've got pressure, we've got volume, we've got temperature, and we've got amount. So these are our 4 quantities that we like to look at. Now what we're going to do is we're going to hold the amount constant. So in other words, this is going to be a constant in all of our situations we're going to talk about right now. So what happens when pressure, let's do pressure versus volume. Okay, so pressure versus volume in a situation, that means that we're holding temperature constant as well as holding the amount constant. So in other words, let's say we have that balloon again, okay? And so we're just going to go ahead and we're going to say, here's our balloon, okay? And we know that inside our balloon, we've got a set number of particles, okay? So there's our particles inside. Now they're in constant motion. They're pushing on the outside of the balloon. And so in other words, what we see then is that the pressure inside the balloon is going to be equal to the pressure outside of the balloon, which means that we have a set volume that we are dealing with. Now, if we we're able to increase the pressure on, say, the outside of the balloon. So pressure inside, pressure outside is the same. So if we said, let's make the pressure outside of the balloon be greater than the pressure that's inside the balloon, that means that all of a sudden pressure outside is pushing on the balloon. It means the balloon is going to have to shrink. So in other words, an increase in the pressure is going to see a volume decrease. And that's where we're going to get a result here. Hold on. Again, as we start to see that pressure is increasing, that means that the volume is going to decrease. The reverse would also be true. As the pressure decreases, so in other words, if we had less pressure outside of the balloon, then that means that the molecules inside are going to create a greater volume. So we would see this, and this is what we refer to as an inverse relationship. So this is an inverse relationship. Now, the next one that we want to look at is we want to look at how the volume relates back to the temperature. And again, now this time we're going to hold the pressure constant. So again, we're going to deal with our balloon. So I'm going to look again at a balloon. Okay, so here's our balloon. And in this case, we're going to say that the pressure outside the balloon and the pressure inside the balloon are always going to be the same. So the push outside here, pressure inside, pressure outside, these are going to be remaining the constant. Now we've got our molecules that are inside of here. Okay, and what we're really going to do is we're going to say, let's take these molecules and let's change their temperature. Now remember, temperature connects back to our kinetic energy. So what we're really saying is that the kinetic energy is going to increase. Okay, that's the motion of the molecules. So that's what it means to see a temperature increase. And if those molecules now are trying to move around faster, that means that they're going to have more energy, more force to interact with that balloon. Now what it's going to do to the balloon is it's going to make that volume increase. So as the temperature of the molecules goes up, that means that we expect the volume of the object to increase. Okay, and that's the only way that we can keep the pressure then the same. So temperature increases, the volume increases. Same thing would be true if we saw the temperature decrease, we would see the volume decrease. So that's a similar relationship. Now because both arrows are going the same way, we refer to this as a direct relationship. Okay. Our last relationship that we want to look at is now when we're going to compare, say, I need to get us a little bit more space. Okay, we're going to compare our pressure and our temperature. And in this case, we're now holding the volume constant. So the volume is not going to change, which means that we're going to look at a container that's now a fixed container. So we'll put some molecules inside of here, some gas particles inside here, and they're going to push on the walls of the container, but the container can't change its size, so the volume is going to be fixed. Now again, as we increase that temperature, we're going to see an increase in the kinetic energy. So this is really just a change in our kinetic energy. Okay, kinetic energy goes up, the motion of the molecules goes up. That means that what we expect them to do is to interact with the walls with more force. Okay, so as they're moving with more force, that means that the temperature is going up. The pressure is going to have to go up as well. So there'll be a greater force on there, so greater pressure on there. Same would be true about if the temperature decreases, the pressure would decrease. And so we would then see this as another direct relationship. And it's all about the motion of those molecules and how they act. In our next video, we'll go into the details of the combined gas law, and we'll do some example problems. But this is kind of our wrap-up then about the activity you did and the kinetic molecular theory.